Today we are continuing our implementation of MakeMore. Now, in the last lecture, we implemented the bigram language model, and we implemented it both using counts and also using a super simple neural network that had a single linear layer. Now, this is the Jupyter notebook that we built out last lecture. And we saw that the way we approached this is that we looked at only the single previous character, and we predicted the distribution for the character that would go next in the sequence. And we did that by taking counts and normalizing them into probabilities so that each row here sums to 1. Now, this is all well and good if you only have one character of previous context. And this works and it's approachable. The problem with this model, of course, is that the predictions from this model are not very good because you only take one character of context. So the model didn't produce very name-like sounding things. Now, the problem with this approach, though, is that if we are to take more context into account when predicting the next character in a sequence, things quickly blow up. And this table, the size of this table, grows, and in fact it grows exponentially with the length of the context. Because if we only take a single character at a time, that's 27 possibilities of context. But if we take two characters in the past and try to predict the third one, suddenly the number of rows in this matrix, you can look at it that way, is 27 times 27. So there's 729 possibilities for what could have come in the context. If we take three characters as the context, suddenly we have 20,000 possibilities of context. And so that's just way too many rows of this matrix. It's way too few counts for each possibility. And the whole thing just kind of explodes and doesn't work very well. So that's why today we're going to move on to this bullet point here, and we're going to implement a multi-layer perceptron model to predict the next character in a sequence. And this modeling approach that we're going to adopt follows this paper, Benju et al. 2003. So I have the paper pulled up here. Now, this isn't the very first paper that proposed the use of multi-layer perceptrons or neural networks to predict the next character or token in a sequence, but it's definitely one that was very influential around that time. It is very often cited to stand in for this idea, and I think it's a very nice write-up. And so this is the paper that we're going to first look at and then implement. Now, this paper has 19 pages, so we don't have time to go into the full detail of this paper, but I invite you to read it. It's very readable, interesting, and has a lot of interesting ideas in it as well. In the introduction, they describe the exact same problem I just described, and then to address it, they propose the following model. Now, keep in mind that we are building a character-level language model, so we're working on the level of characters. In this paper, they have a vocabulary of 17,000 possible words, and they instead build a word-level language model. But we're going to still stick with the characters, but we'll take the same modeling approach. Now, what they do is basically they propose to take every one of these words, 17,000 words, and they're going to associate to each word a, say, 30-dimensional feature vector. So every word is now embedded into a 30-dimensional space. You can think of it that way. So we have 17,000 points or vectors in a 30-dimensional space. And that's, you might imagine that's very crowded. That's a lot of points for a very small space. Now, in the beginning, these words are initialized completely randomly. So they're spread out at random. But then we're going to tune these embeddings of these words using backpropagation. So during the course of training of this neural network, these points or vectors are going to basically move around in this space. And you might imagine that, for example, words that have very similar meanings or that are indeed synonyms of each other might end up in a very similar part of the space. And conversely, words that mean very different things would go somewhere else in the space. Now, their modeling approach otherwise is identical to ours. They are using a multi-layer neural network to predict the next word, given the previous words, and to train the neural network, they are maximizing the log likelihood of the training data, just like we did. So the modeling approach itself is identical. Now here they have a concrete example of this intuition. Why does it work? Basically, suppose that, for example, you are trying to predict a dog was running in a blank. Now suppose that the exact phrase, a dog was running in a, has never occurred in the training data. And here you are at sort of test time later, when the model is deployed somewhere, and it's trying to make a sentence, and it's saying a dog was running in a blank. And because it's never encountered this exact phrase in the training set, you're out of distribution, as we say. Like, you don't have fundamentally any reason to suspect what might come next. But this approach actually allows you to get around that, because maybe you didn't see the exact phrase, a dog was running in a something, but maybe you've seen similar phrases. Maybe you've seen the phrase, the dog was running in a blank. And maybe your network has learned that a and the are frequently are interchangeable with each other. And so maybe it took the embedding for a and the embedding for the, and it actually put them nearby each other in the space. And so you can transfer knowledge through that embedding, and you can generalize in that way. Similarly, the network could know that cats and dogs are animals and they co-occur in lots of very similar contexts. And so even though you haven't seen this exact phrase, or if you haven't seen exactly walking,
So I think yesterday we were learning how to embed these vectors, right? I think it goes a bit like that. But I'm just trying to make a sense out of it. So when we put an input, right, each word will be an embedding. So next word we can make those predictions. Okay. I think till now what I have learned is how we can embed or how we can create embeddings for different word given a context words, right? um, how the next will be predicted by gram I still know. So anyway, I'm not sure.
or running, you can, through the embedding space, transfer knowledge, and you can generalize to novel scenarios. So let's now scroll down to the diagram of the neural network. They have a nice diagram here. And in this example, we are taking 3 previous words, and we are trying to predict the 4th word in a sequence. Now, these 3 previous words, as I mentioned, we have a vocabulary of 17,000 possible words. So every one of these basically are the index of the incoming word. And because there are 17,000 words, this is an integer between 0 and 16,999. Now, there's also a lookup table that they call C. This lookup table is a matrix that is 17,000 by, say, 30. And basically what we're doing here is we're treating this as a lookup table.
Yeah, so we are trying to fetch the embedding for that particular word.
And so every index is plucking out a row of this embedding matrix so that each index is converted to the 30-dimensional vector that corresponds to the embedding vector for that word. So here we have the input layer of 30 neurons for 3 words, making up 90 neurons in total. And here they're saying that this matrix C is shared across all the words. So we're always indexing into the same matrix C over and over for each one of these words. Next up is the hidden layer of this neural network. The size of this hidden neural layer of this neural net is a hyperparameter. So we use the word hyperparameter when it's kind of like a design choice up to the designer of the neural net. And this can be as large as you'd like or as small as you'd like. So for example, the size could be 100.
So in neural networks, we have seen, right, the middle layers, we can decide how many um, those neurons we want to have. That can be any number.
And we are going to go over multiple choices of the size of this hidden layer, and we're going to evaluate how well they work. So say there were 100 neurons here. All of them would be fully connected to the 90 words or 90 numbers that make up these 3 words. So this is a fully connected layer.
Okay, so looks like what they're what in the paper they're proposing is this 90 90 90, we put them in a large array of, I mean, sorry, 30 30 30, we put them in a large array, we just concatenate, they become 90, and that's how we represent 3 words, and that will be the input, and anyway the output we will be expected. Anyway, that's simple.
Then there's a 10H long linearity, and then there's this output layer. And because there are 17,000 possible words that could come next, this layer has 17,000 neurons, and all of them are fully connected to all of these neurons in the hidden layer. So there's a lot of parameters here because there's a lot of words. So most computation is here. This is the expensive layer. Now, there are 17,000 logits here. So on top of there, we have the softmax layer, which we've seen in our previous video as well. So every one of these logits is exponentiated, and then everything is normalized to sum to 1, so that we have a nice probability distribution for the next word in the sequence. Now, of course, during training, we actually have the label. We have the identity of the next word in the sequence. That word, or its index, is used to pluck out the probability of that word, and then we are maximizing.
So we put that 90, say it gives me a prediction of all the seventh, or probability of all the 17,000 words, but we know that something like something like a building make more part to MLP, let's say. So we are giving our model input building, that is the 30 feature size representing building, 30 feature, 30 size matrix, feature matrix for make more, 30 size feature matrix for ML part 2. When we put in there, it gives me a prediction. Um, we know that the next word is MLP, but it, say the model gives the probability of 0.2, and there's a difference, and we calculate the loss, that is the negative loss, negative log likelihood, means how far it is from 0, us the error and we backpropagate. And we keep on doing that for the whole text that we have.
The probability of that word with respect to the parameters of this neural net. So the parameters are the weights and biases of this output layer, the weights and biases of this hidden layer, and the embedding lookup table C. And all of that is optimized using backpropagation. And these dashed arrows, ignore those. That represents a variation of a neural net that we are not going to explore in this video. So that's the setup, and now let's implement it. Okay, so I started a brand new notebook for this lecture. We are importing.
So there's a new. I think the names are here. These Karpathy sir is writing comments if I don't write it. That's that will be a huge disrespect. So usually split lines, right? It gives you in the form of array. Else you will get something like this. So this slash n, right, is the new line character. So it splits using this and creates an array. If we do like this, right, and this will be a huge array, and looking at the first 8 words there, and the number of characters those are there is 30,000. Now it is trying to build a vocabulary. So I think this is something we are seeing during that CS 224. No, sorry. I was looking into how we create embeddings and everything, and so we create this huge vocabulary array where we tell that for each now we assign a number to a word so that other functionalities and everything, right, becomes much more simpler in coding or in Python, because it makes life a bit easier. Okay, so the first is doing, so this is a way to So usually what I think we can okay. Oh, I took the finally. So what this does is it, if you see right, it's just combining all of them. Yeah, means my system might crash. So list is each of the letters that you are seeing, right? It is taking so it will be like this array where the first will be E, then M, then A, then O, like this. It will be a huge array. Oh, okay, so before that itself it is doing the set. So what set does is it first identifies all the unique characters in there, then it converts it to a list. So what it will happen is E, then M, then it will see okay, M is already there, no need to take M again, then A, O, L, I, V, then again it will see I has already been read, don't take I, A has been already taken, don't take A, like that it will go. So it will identify all the unique characters in this word and then return a list out of it, and then we are making it sorted. So sorted will be I think in reverse order or something. Let's see. Sorry. Mm, 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 mm. This alright. So in the whole of the vocabulary, it took what all unique characters was there, sorted it, and string to index something like that, and we are going to assign to each character, right? Number. So enumerate, what it does is it will give you first character obviously, and then a number, so 0. So if I write for I comma j in this, right, so I will be 0, j will be a. Next iteration, I will be 1, j will be b. I will be 2, j will be c. That's how it goes. And it is saying yes, sorry, j. So these braces, right, helps create a dictionary, and in that dictionary, right, we are saying go through this. So for the first time when this for loop is run, right, pluck out the character, that is the j, a, and assign it I plus 1. So it will be 0 in the initial but have 1 there. The reason being that we'll see in some time. So this is how it is, okay, all the unique characters. So it took the characters and everything because he wants to initialize that dot as well, what we were doing in make more, right, and creating the ulta as well. It it is we already saw where it is getting you, so you don't need this one. So for I comma j in so sorry, j comma I. So you can see in the first we are taking the number and assigning it a it's the character, and here we are doing the ulta. Both will be used. So that's still that time.
PyTorch, and we are importing Matplotlib so we can create figures. Then I am reading all the names into a... Keep in mind that we have a 32,000 characters, and all the mappings from the character to do is we want to compile the dataset for the neural network. And I had to rewrite this code. I'll show you in a second what it looks like. So this is the code that I created.
So let's go through that. Block sizes in bigram. We have one context size. What that meant is if E is there, if E is there, we're trying to predict M. So you can say the context size was just one. So only one character we are looking, and we are trying to predict the next. So here we are trying to do 3. I think you can change it to anything. It will work, I believe. Taking the first 5. Sorry. शराब कैसी सो- Let's see what he's doing. So he takes the first word. He's creating an array of size 3, initializing it to 0. Means an array which has 3 elements and all 3 are zeros, which he's giving the name as context. He's going through each character, but for that he's adding a dot as well to represent the end of the word. That's nice. Then it takes the character, the index of that character from this array for that character. We have two arrays here. In one array he is appending the context, in the other he is appending the index, kind of, you can say. For for a right, for a right in one of the array y, it has a corresponding entry in the X array for the context. So anyway, we'll print out what we're seeing here. Print So first he's printing for I in context. Context, there is nothing, so it's basically 0, and is plucking out that 0th element from there and doing a join analytic. I think what anyway, this NITUSIX context 1 afterwards. Let's see what's happening in here. So here we are printing the word. Okay, so initially context is all zeros. Got it? So obviously when for I in context it gets a 0 because print it as well. Just let it run for one iteration so that we can understand. Context that it is printing. Let's print context here as well, and X and Y will print later. Okay, so see, first we took the Emma, and this context is all 000, block size of size 3. X, it input the context word, so X is a 2D array, we'll see later. This also we'll see later. So for I in context, because it took 0, right, ITOS of 0, so ITOS of 0, it gives a dot, so it gave a dot, 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 so this represented 3 dots. Okay, this sign, and then ITOS of IX. So and that character was E anyway, so that's what we fetched. Then what we did was context 1 after plus ix. What was ix? Okay, sorry, let's spread this as well. Okay, so it took the first character E, and for that the index was 5, and it put 5 there, print the context. Next time when it went, it took the other character M, whose index was 13, but now the context has already 5 in there, so z so the context array is 0 0, so you see 2 dots, but then it is 5 from the previous iteration, and 5 is E, so it prints that for. Okay, I got it. I think I get it. Okay. So it found 13, it put in 13 there, so now it has 5 and 13. The next iteration, again it got M itself, so again 13, so again we put it in there. Now A has 1, so we found got 1. We inserted that itself, and again we inserted D, it's a 0. So what he's doing, right, rather than going through all of this, we can print X and Y as well. Shut up. Someone can. Okay. So for E, right, we are storing two things. One is the context vector for that, because nothing comes before this, right? Before E, there is nothing. So we store 0 0 0. That is the context word for E. Okay, I mean, as if like 3 characters before E, right? What are those? So those are dots. We have already seen E now. Now for M, right? The next. This was for E, this is for M that is getting stored in there. So what is happening for M, what we have seen E, and then dot dot we have seen. Okay, because we have seen E already before this and there was nothing. So 0 0 0 representing dot, 0 representing dot, 5 representing E. Then we find M. Okay, so okay, so M, so for now for this M, right, we have seen M, we have seen E, and we have seen a dot, because 3 is the context size. So this is the context for this three characters before that. So this is for that. So we have seen 13, that is already an M, 5 is an E, and then a 0. Again after this we come to A. Okay, so for A we have seen M, M and E. M is again 13, M is 13 and E is 15. So context vector for A is M, M and E, that is 13 13 5. After that we were inserting a dot as well to represent the end of the character. So before this what we have seen, A M M A, so that is like here the dot is here, so A M M. Okay, A is 1, M is 13 13, so see, you see 1 13 13. So we are building two arrays. One is, this is the X array where we are storing all the context word for these characters in there. But my only thing is that 13 should just come once here. Why it is coming twice? But anyway, let's see. So when we do for 5, right, it'll be pretty huge. But that's what you get. See, Just keep increasing. So we have seen these many characters. For each characters, these are the context arrays. That's what it is saying. So for each word, what are the contexts?
For the dataset creation. First, we're going to define something called block size. And this is basically the context length of how many characters do we take to predict the next one. So here in this example, we're taking 3 characters to predict the 4th one. So we have a block size of 3. That's the size of the block that supports the prediction. Then here I'm building out the X and Y. The X are the input to the neural net, and the Y are the labels for each example inside the X. Then I'm iterating over the first 5 words. I'm doing first 5 just for efficiency while we are developing all the code, but then later we're going to come here and erase this so that we use the entire training set. So here I'm printing the word, Emma, and here I'm basically showing the examples that we can generate, the 5 examples that we can generate out of the single sort of word Emma. So when we are given the context of just dot dot dot, the first character in a sequence is E. In this context, the label is M. When the context is this, the label is M.
I think, yeah, I told you that if we have seen dot dot dot, let's think it that I told, I think E, and then we are seeing dot dot dot. So if we are seeing dot dot dot, the next word that should be predicted is E. If we have seen dot dot E, the next word should be predicted is M, like that. So E M M, if we have seen, A should be predicted or something. That's how it is, but okay.
And so forth. And so the way I build this out is first I start with a padded context of just 0 tokens. Then I iterate over all the characters. I get the character in the sequence, and I basically build out the array Y of this current character and the array X, which stores the current running context. And then here, see, I print everything, and here I crop the context and enter the new character in a sequence. So this is kind of like a rolling window of context. Now we can change the block size here to, for example, 4, and in that
So one dot usually what it does it, right? You can say it's something like, sorry, 0, 1, 2. Okay. Equal to that, sorry. Okay, 0, 1, 2, A. You understand what it is doing? So it pushed this out one of the array, and then it added one more thing. So you can say 5. So what it did, it pushed this thing up and added one more thing here. So that's what he's doing here.
in that case, we would be predicting the 5th character given the previous 4. Or it can be 5, and then it would look like this. Or it can be, say, 10, and then it would look something like this. We're taking 10 characters to predict the 11th one, and we're always padding with dots. So let me bring this back to 3, just so that we have what we have here in the paper. And finally, the dataset right now looks as follows. From these 5 words, we have created a dataset of 32 examples, and each input to the neural net is 3 integers, and we have a label that is also an integer, y. So x looks like this. These are the individual examples, and then y are the labels. So given this, let's now write a neural network that takes these x's and predicts the y's. First, let's build the embedding lookup table C. So we have 27 possible characters, and we're going to embed them in a lower dimensional space. In the paper, they have 17,000 words, and they embed them in spaces as small dimensional as 30. So they cram 17,000 words into 30-dimensional space. In our case, we have only 27 possible characters, so let's cram them in something as small as, to start with, for example, a 2-dimensional space. So this lookup table will be random numbers.
So understand what he's saying, right? So he's saying that for all these 27 characters, right? Each word be represented by 2 dimension or 2 features. Usually you can think of it this way, say I Abhishek, right? And there is Andrew. How you specify or how you can pinpoint that you are talking about me? Let's say you give me a name, Abhishek is one feature, Abhishek, but it might happen two people can have the same name as Abhishek. So you tell them one more feature as I don't know, DNA structure or something that helps you with that or something like that. But any other thing means say height. Let's just take height is 5'8" and the other Abhishek has 5'6". Just very crude way. So these are the two features that you are using to specify me Abhishek and that other Abhishek. So in the same way he's saying here, so how, or if we have to specify Andrew, right? It will be Andrew and his height, say 6. Okay. So like that, every individual will have these two features that will be sufficient enough to say, or we can distinguish between two people. So that if we just look somebody's name, Andrew and height, we know about whom we are talking about. So that way he's saying that for each of these characters that you see, right, we want to create an embedding. Embedding means that how we want to represent each of these uh, letters. So when for E, right, here he's saying we'll assign two features. Hmm. We, and why two? There is nothing, means it can be anything. In that paper, it was 30. It took, we can take anything that helps us represent that. But the bottom line is that embedding for each character tries specially represents E. We will, in the same way, we'll have the embedding for M, which will be two elements or two features. So that two feature, the numbers that will be there in those two features, right, will help you specify M. Those two feature, A again will have array of two elements, those two features, and those two features, the value in those, right, will specifically represent A, and that won't be similar for all. So for A, for sure it will look different. M, it should look different. O, it should look different because they are different. Okay.
And we'll have 27 rows and we'll have 2 columns, right? So each one of 27 characters will have a 2-dimensional embedding. So that's our matrix C of embeddings in the beginning initialized randomly. Now before
Okay, and sorry. Okay, so here you can say this is what will get trained as we go ahead in neural net, but as of now it is trying to say the first 0 it is dot say. So 0 is represented using these two numbers and these are different. Again for A, B, that is how you're representing all of this. And as of now these are all random numbers, but we'll train this and everything so that we get proper embedding for this array.
Before we embed all of the integers inside the input x using this lookup table C, let me actually just try to embed a single individual integer, like say 5. So we get a sense of how this works. Now, one way this works, of course, is we can just take the C and we can index into row 5. And that gives us a vector, the 5th row of C. And this is one way to do it. The other way that I presented in the previous lecture is actually seemingly different, but actually identical. So in the previous lecture, what we did is we took these integers and we used the one-hot encoding to first encode them. So f.1hot, we want to encode integer 5, and we want to tell it that the number of classes is 27. So that's the 26-dimensional vector of all zeros except the 5th bit is turned on. Now, this actually doesn't work. The reason is that this input actually must be a Torch.tensor. And I'm making some of these errors intentionally just so you get to see some errors and how to fix them. So this must be a tensor, not an int. Fairly straightforward to fix. We get a one-hot vector. The 5th dimension is 1, and the shape of this is 27. And now notice that, just as I briefly alluded to in the previous video, if we take this one hot vector and we multiply it by c, then what would you expect? Well, number one.
So this is so what this does is, right, so see if you see, right, so it will pluck out the fifth 0, 1, 2, 3, 4, 5. So it will pluck out this from the because 1 is present there, right? So it will pluck out that index.
Number one, first you'd expect an error because expected scalar type long but found float. So a little bit confusing, but the problem here is that one hot, the data type of it, is long. It's a 64-bit integer, but this is a float tensor. And so PyTorch doesn't know how to multiply an int with a float, and that's why we had to explicitly cast this to a float so that we can multiply. Now, the output actually here is identical. And that it's identical because of the way the matrix multiplication here works. We have the one hot vector multiplying columns of C, and because of all the zeros, they actually end up masking out everything in C except for the fifth row, which is plucked out. And so we actually arrive at the same result. And that tells you that here we can interpret this first piece here, this embedding of the integer. We can either think of it as the integer indexing into a lookup table C, but equivalently we can also think of this little piece here as a first layer of this bigger neural net. This layer here has neurons that have no nonlinearity, there's no 10H, they're just linear neurons, and their weight matrix is C. And then we are encoding integers into one hot and feeding those into a neural net. And this first layer basically embeds them. So those are two equivalent ways of doing the same thing. We're just going to index because...
So here he is saying either you directly give C of 5, which is taken up here, or before these you do this multiplication, you convert it to one hot, multiply it with C, you are getting the same result anyway. So these are the two ways of doing it.
It's much, much faster, and we're going to discard this interpretation of one hot inputs into neural nets, and we're just going to index integers and create and use embedding tables. Now,
so he's saying that the one hot multiplying that introduces one more level of calculation. Why you want to do that rather than directly using that index pluck out its embedding.
Now, embedding a single integer like 5 is easy enough. We can simply ask PyTorch to retrieve the fifth row of C, or the row index 5 of C. But how do we simultaneously embed all of these 32 by 3 integers stored in array X? Luckily, PyTorch indexing is fairly flexible and quite powerful. So it doesn't just work to ask for a single element 5 like this. You can actually index using lists. So for example, we can get the rows 5, 6, and 7, and this will just work like this. We can index with a list. It doesn't just have to be a list, it can also be actually a tensor of integers, and we can index with that. So this is a integer tensor 5, 6, 7, and this will just work as well. In fact, we can also, for example, repeat row 7 and retrieve it multiple times, and that same index will just get embedded multiple times here. So here we are indexing with a one-dimensional tensor of integers, but it turns out that you can also index with multi-dimensional tensors of integers. Here we have a two-dimensional tensor of integers. So we can simply just do C at X, and this just works. And the shape of this is 32 by 3, which is the original shape, and now for every one of those 32 by 3 integers, we've retrieved the embedding vector here. So basically, we have that as an example. The 13th, or example index 13, the second dimension is the integer 1 as an example. And so here, if we do C of x, which gives us that array, and then we index into 13 by 2 of that array, then we get the embedding here. And you can verify that C at 1, which is the integer at that location, is indeed equal to this. You see they're equal. So basically, long story short, PyTorch indexing is awesome, and to embed simultaneously all of the integers in x, we can simply do C of x, and that is our embedding, and that just works. Now let's construct
So it constructed the embeddings for. Okay, so there are two things to it. One is, so you realize there are two arrays that are coming into the picture. One is the context vector, the other is the embedding vector. Okay, so context vector is, if we have seen a word, what are the corresponding context for that word? Okay, and the embedding is a in itself, how you are representing. So if I do say C of 0, that is the embedding, how you are representing. Say C0 represents a dot, so dot is represented using these two words. Okay, and when we do a x of 0, it represents 0 0 0. Let's take a different example where you see some numbers. Yeah, 4 is, I think, D. Sorry. I have some confusion here. Let's go through it once more. So X is a 2D array, okay, which represents, is not taking into account the y. Okay, got it. How it identifies that? Let's, this already we have seen.
enough. We can simply ask PyTorch to retrieve the fifth row of C, or the row index 5 of C. But how do we simultaneously embed all of these 32 by 3 integers stored in array?
So you understand what he's saying there? So he's saying that it's a 3D array. Or But sorry, yes, it's a good way. Oh, so it has two dimensions. Let's take it as three, and then that is two. Just bear with me a bit. Oh, not sure. Um, okay, anyway, I will explain using this itself. So see, what is happening is, first let's talk about x, okay? So x has 30, what is the shape of x? 32. So think, as of now, I'm not able to change values, but 0, 1, 2, like this, think of it, we have, okay, we have 32 here, and on the other side, we have 3, okay? So that what that represent is, we have seen such 32 characters in whole of our training data. If we take the first 5 words, so 32 we have seen um, words coming in here, and for each 32 words, right, we have 3 features, so 0, 1 and one more 2. Okay, I'm not able to change the size here, so um, or means 3 context words. Okay, so I am trying to show you the x part of the things. Okay, this part, so we have 32 like this, so that's 32 element in this side and 3 in this side representing this. So first you can expect this to be 0, 0, 0. Okay, then this here will be 0, 0, 5. Like this you will have 32 such 3 size array. Okay, now what he is saying, each of these words 0, 0, whatever you see here, right, here it shows you as uh, 10 is being stored here. Okay, what he is saying, 0, right, 0 represents a index. Okay, index of a letter. So here, right, 0 is representing dot. Okay, 5, which we see, right, represents E. 5, 13 represents EM. Now each of these 0 at E has its embedding stored here. Okay, so uh, 0 represents E dot, right, so it has its own embedding. This is what is embedding of this. 5, right, has its own embedding. 0, 1, 2, 3, 4, 5. 5 has its own embedding. 13, right, somewhere it will be 13, has its own embedding. So for each of these, right, will store its embedding in the other layer. Getting it right. Um, so here we are storing the context across these two axes, and in this axis, right, we are storing for each of these letters for 0, so it will be 0 0 0, right? So in this side, right, we'll store this minus 1.1.31, again minus 1, because all are zeros, right? These three zeros minus this same array will be stored here, here, here. When we go to this side, okay, if we see from this side, right, that will be 0 0 5. So first will be for 0 minus 1.1, next will be again minus 1.5 minus 1.5, and the third that stands here, right, will represent 5. That is this one will be stored in this side. So he's storing the context, whereas the embedding for those as well. So that's what you are getting it here. So he's saying if we do it something like this, because at the end of the day, right, what X store is the indices. So for each index, for each X00, okay, it tries to fetch, um, so for I, sorry, okay, how do we treat over a list? It's a 2D array, right? So I'm not sure how you do that, but not that great. Literally, I should learn how to. Sorry for that. Just trying to. Yeah. It's not working. Anyway, okay. So, leave it. So how that is going at x 0 0, first it's taking, okay. So this returns you 0 because it's a dot. X 0 1 returns you again a 0 because this is 1. If you want to see this E, right, we have to go 0 1 and then 2. So it will be 1 2 5. So you got this 5. Now what it is doing, he's inputting this 5 into the C. Okay, C5. What that's happening is it's returning the indices. So we are putting each of these elements, each of these elements 0 we are putting into C, fetching the embedding. 0 we are putting into C, embedding the fetching. 5 we are putting into it and embedding the embeddings. So that's where when you put this X, you get a huge array. And this, see, it represents 0 0 0 0 0 5. This is dot 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 E dot E, again E came. Oh no, sorry, M came, sorry. So dot e m, then here e m m. That's why the both are same. So for whole of that X array, right, we fetch the embedding in here.
So 5 like 7. It doesn't just have to add times. But it turns out 32 by 3, which is the original shape, and now
So 32 by 3 for each of those 0, 0, 0, 0, 0, 5, for each of these elements in X, right, we are fetching
for
this.
everyone. So basically, we have that 13. And so here 13 by 2. And you can verify that is indeed long all of the integers it works. Now let's construct this layer.
So that's embedding. Actually, in the other place, just to avoid this confusion, right, usually other places I was seeing that they maintain two different arrays. One is the context and embedding. Here it is putting it on top and maintaining it as one array. But in other places, right, less confusing. I felt that was where we were maintaining two arrays. But anyway, this video has been a lot. It has already crossed an hour or so. So we'll go over it